And if you want to get the same parameters, you should train it. So switch it on and do some manipulations. Then after some heating, the parameters will move up to the level.
But can we have any information on how to do it?
Not to ruin it.
I don't know how. But my boss very probably, tomorrow morning he's very busy. But he can probably come tomorrow afternoon about 2 o'clock here to the laboratory.
Okay.
He's a good friend of Vyacheslav.
Okay.
So
Like,
at least he possibly tell you something and maybe
Thank you. Thank you.
Окей. So, we'll discuss new development or field development to the array for advanced cosmology experiment, but really the question is what to do and where to go with parameters. And main idea will be to expand size of array. We discussed with you some time ago. Is it good or not to have large array? Because
It is good.
good, it's good.
Yes, it's
Power
easy
is
to
larger.
answer.
No, only one suspicious how it will be, maybe over saturation of bolometers or not. But in our case, it's simply expanded and
Yes.
the split power, and it's only good. Yes, answer will be very well confirmed this idea. So I will inform about this experiment for polarization measurements, that means for boomerang. And then we are doing some background concept for spike and maybe for millimetron in cooperation with Phil Mauskov. And also it can be used possibly for your FTS that you are doing. And it's shortly inform about this information. Then it's interesting that we were asked recently by Kardashov, could we do photon count for 20 micrometers? But it's a separate question. I simply inform you that this question is in stage of discussion.
Very interesting.
Maybe I will not have time today. But anyway, we are thinking now about this realization also, and it's type of photon counter for 20 micrometers. So the idea with this array, it's long time idea, but a new step was after meeting with Peter Day from Caltech and Phil Mauskov, and we decided to test this series array of bolometers. Series, I mean DC series, but in all arrangements it's always this 2D arrangement for high frequency. So we split power, we collect signal from series array, we increase responsivity, and we can get quite good characteristics as shown here. Total NEP is less than photon noise. It's mainly limited still by amplifier. We are thinking about JFET amplifier with these parameters. And of course it looks quite good, but not maybe very perfect, not very reliable, because it's small scale array. And if we violate something, or this noise, or responsivity of bolometer, maybe we wouldn't have this good realization. And then again, question about polarization resolution. We need for that goal as large as possible array. And we prolonged this work, and second step was to avoid series array. We have some parallel series combination of this array for DC, for matching with this amplifier, for reliability. No, it's quite good realization also. Characteristics are quite good. Different combination of bolometers here, and again, all of them are less than photon noise. So in that step, we thought about two sections for one polarization. It's easier from technological point of view, but it's not so perfect for polarization. It's some disturbance. We only have half of power here, another half is here, another half will influence on this part, and so on. And we start to think about further prolongation of this development. It's some formulas, noise description. And you see, when we made first experiment with this array, we got quite good responsivity. So it's signal at the level of 3 microvolts. It's quite good for our measurements. And we create 8 by 8 each segment, that means 128 bolometers total. And we can see very reliable realization. You see very good structure of these bolometers, very clean, no problems. No, that means it's simply, I confirm this statement that if you have good realization for one element, for one bolometer, really no problem to create large array. It's quite repeatable, and then it's very resistive to any influence, to interferences, to spikes, and so on. That means this decision in this case is quite perfect. So then comparison, for example, responsivity for this 2D array, you see level 6 microvolts, with typical experiment with cross-slot antenna. It's 1 order of magnitude less. So it's considerably more difficult to concentrate, to align, and so on. That means all our speculations today confirm this line that maybe 2D array is very perspective and attractive direction of our development and realization. So, this experiment was made, first it was made without filters, then we put filters for 350 Hz, but the result approximately the same. Because our suspicion was maybe it's too wide bandwidth and we can some other signal, but fortunately it's more or less okay for this realization. And then finally, that we discussed today also, it was moved to this realization. It's really overcross of two polarizations through capacitance. It's exactly on the same place, exactly the same temperature, and all these precautions about different directions, I suppose, will be not related to this realization, because they are in the same place and the same substrate. We hope it will be very good and reliable realization. We are now analyzing the system, and Stanislav is doing simulation for cross-polarization. But anyway,
how do you make the bridges? I mean, the crossings.
The crossings, usually we put, there are two ways. One, insulation made exactly by aluminum. Simply we open chamber and aluminum is oxidized, and it's really enough for oxidation. But then we find sometimes problems. We are not sure exactly with this one. We put also additional layer of silicon monoxide or silicon dioxide. In this case, it's twice reliable. And there are options to do overcross of electrodes as it is, or to do more narrow lines and overcross of these lines. No, possibly we'll do second option, and it's simply easy technologically and maybe better for cross-polarization. So, and you see it was suggestion of classical realization when we have this substrate with anti-reflection coating, not shown here. This is structure, and then some backshot from another side. Again, we have good, relatively good realization, but question how to improve, how improve realization and have additional, spare parameters if we spoil something, anyway to have good realization. So, question where to go and how to create the most effective system. And this is the question, how we can win competition, radioastronomically was, and where to go. And you know, Paula, in this case when we put this equation, where to go, we have many pictures in Russian folk tales, when this knight is thinking where to go. And you see, there are several options, to be rich on the left, to be married on the right, and to go for something unusual and could be killed even when he occupied new area and so on. We decided to go straight ahead.
Okay.
What will be fine. That means okay, not like to be rich, not like to be married, but like to be, I don't know, to win something. So, the same array, but we will expand this number of bolometers and see influence on properties. And there are three parameters of bolometers: efficiency of quasi-optical coupling and polarization resolution. NAP of bolometer itself and NAP of amplifier. And I will show that this way will improve all three parameters of this system. That is quite attractive. The basic idea is shown here. If we increase size of this system array, increase number of bolometers, it's shown on this axis total number and square of bolometer of this system. So we unavoidably increase power proportionally, linear proportionally to this number of bolometers. And photon noise is square root of this power. That means it's slow increase. That means difference or ratio between them will be better if we increase size of bolometer. This is basic idea that we start to think about all realization. That means this fundamental limitation, fundamental parameters will be improved. And then we can see influence on properties of bolometers, NAP of bolometer, amplifier, and so on. So this diagram is showing this realization. You see again number of bolometers, then total power that we discussed, then NAP of photon noise, I mean total, it's simply total NAP, sorry. NAP of photon noise that was shown before, and then NAP of bolometer. In this case, for this realization with these parameters of JFET amplifier, we have this noise here even a little bit less than photon noise. It's good. But you see, if we increase number of bolometers, the ratio between them is better. And on this way, we practically don't have increase of amplifier noise. It's a small change only due to change of bias point. A bias point should be changed because we should do matching of bolometer and proper differential resistance. So it's some small tuning. If you don't have this tuning, it would be the same amplifier noise, but it's a little bit changeable. And that means contribution of amplifier noise is less and less. For SIN junction, it's a little bit more because they should consume energy and transfer to electrode. NAP of electron phonon part is very small because we managed to very small absorber that is very good for both, for decrease of this noise, electron phonon noise, and for this dangerous from cosmic rays. So it's due to very small volume of absorber. Finally, you see, this ratio between phonon noise and CB noise is better. And if we check this fluctuation resolution, temperature resolution, that is divided from this formula, we can see this temperature resolution is improved also when increased number of bolometers. Again, this blue one, it's fundamental limit, it's due to photon noise, it could not be better. But due to our bolometer influence, it's a little bit higher, not too much, but anyway. And for large number of bolometers, we have quite good realization. It's full for microkelvin for square root of units. So now, maybe it's more technical parameter, but really more important for our experiment, it's amplifier noise. And, well, you know, our idea is to realize this system with room temperature amplifier for 90 pixels and 180 amplifiers. If you manage to do it, of course, it would be great advantage.
So how many wires?
In principle, if we use 2 wires for voltage and maybe one couple of wires for current bias, it will be 320 plus 2.
It's marginal. I mean,
Yeah,
it's not impossible because in the Olimpo cryostat we had
No, well, also in Lumen and Preston we had the 440 wires,
Yes.
and
Yeah,
that was fine. So
340.
if it is less than that, or
But there is a specification for the wires, or is not? I mean, we are using stainless steel wires.
Why?
Stainless steel
Yeah,
wires.
no, why stainless steel?
Because low heat load.
Yeah, okay. But you mean some resistance?
There is some resistance.
What
I mean,
resistance?
the wires are maybe a few hundred ohms.
No problem. We have the same.
Because,
We have
yes, I
the
mean,
same. We have manganese wires. The same, but anyway, even for voltage channel, we put the resistance by 100 kilo ohms. That means it doesn't matter too much.
Yes, I mean there is some noise from the wire itself, from the yes. But,
Yeah. But no, I don't think it will be important. So because anyway we have. No, it's typical for our experiment also. This level.
yes, I mean it's difficult to have less
Yes.
than
That
maybe
means simply idea.
typical 500 ohms. This is
Yes,
typical
yes.
for
Idea
one wire.
is to try to do it more problem with microphonics and this additional noise.
Yes.
And this is why our very important to have some reserve for parameters.
Yes.
Loss noise of amplifier not so important. And I will illustrate how it can be realized with this system. You see, it's two type of amplifier noise. This is ideal for AD743 when we use two amplifiers. And let's say that both components are increased 2 times. Before we had this photon noise and this amplifier noise. In that case, amplifier noise start to be larger than photon noise, and total CAB noise larger than photon noise. It's not so good. But when we move to larger number of bolometers, we compensate this, and you see photon noise is increased, amplifier noise is quite low, and even if we have additional microphonics noise or something, maybe we can realize still good system.
Yes.
So, and the same for delta T, fluctuation sensitivity. Now it's difference more from photon noise to full system noise. But again, if we increase number of bolometers, we move down and not so far from photon noise is realization. That is good. So that means we try to push this way, very reliable, very straightforward way, and very easy for realization with room temperature amplifiers. So that means it's one additional option that can help us to do it.
No, it's very important that we don't have to mess with JFETs, cold and...
Yeah, I know. I read your articles, even power budget for 30 amplifiers. It's already a problem.
Yes, it
Compromise between noise, bias current, and
Yes.
power budget. And in this case, it will be easy to realize. There was no problem with this.
Yeah, and yes, I mean, it looks great.
Oh,
Go
yeah.
ahead.
We are looking forward to realize the system. If we move to this scale, maybe it will be very good. So the scale, I would say around 60 by 60 or maybe 20 by 20 amplifiers. It will be pixels. It will be already quite good realization.
So how critical is to increase the number of junctions? I mean,
No, so far we found out opposite tendency. When we start to do it, there were some problems with lithography, but when we achieve clean lithography, main lithography, so it's quite reliable. And then we are doing this arrays, and whole array is working. And in that case, opposite. We found out that stability and yield of this array start to be better than for single junction. Single junction can be very easy burnt out, and some interferences also are influenced for that. Also, when we compare our 4-junction structure, single junction structure, and array of 64 or 128 bolometers, we see for this 128 perfect IV curve. That means all of them are the same, ratio 1000. When we see it for this single structure, it's not so good. More smeared, I don't know, is it a little bit burnt out already, or it's smeared by fluctuations or something. That means it's not a question of this scale as it is. It's a question that when we have very reliable lithography, first of all, then we are doing some evaporation, lift off and so on, it's okay. Of course it consumes some time for exposure, but anyway it's enough. So when we do this structure, it's quite reliable. And then if, let's say, one junction is burnt out, it still be a workable system, because it's only, I know,
Yes.
12% or something will be destroyed.
Yes,
It depends on our combination. It's more reliable system. That is important, very important for future.
So this means that the yield of this process is very, very high.
Yes.
Because
Yes. It's very high, and especially inside of one structure, it's extremely high.
Yeah.
It's not so good between structures, but if you do something and for one structure and many junctions, you are doing. For another technology we've made just for thermometry, we now start to discuss now, we made 400 junctions, and also quite good results. So that means if you move in that direction, we can create quite reliable system, and yield is quite good. And we improved some technology. There was some modernization of technology, even new type of technology, advanced technology for the shadow operation. And I informed people, I recalled your words when we met in Rome and discussed all this plan. Final, your question was, Leonid, bolometers should work.
of course.
When we arrived to South Pole, I remember this, and I repeat to our colleagues, bolometers should work. When we arrived, whole team, we scanned some gallium and so on with all equipment. Yes, it should work. This is one step, good step in the direction. Second step also will be good to cover by silicon monoxide to do passivation for this anti-reflection coating. And all the steps will improve reliability and yield. So let's hope it will be good and reliable system.
Yeah, I'm so impressed by all these activities that.
Thank you.
No,
Thank you.
sure.
Then I repeat simply the same as already Stanislav brought. No, it's
Yes.
simply information about realization of these parameters. No, it was already
Yes,
you was
discussed.
involved. And then some activity with FieldMOScope for Safari, that European instrument. And we also discussed with Peter Day about BLIS, possibly, but mainly about Safari. This realization for Safari, various complicated TES, suspended legs, very complex system, because there should be very, very small conductance between electrons and phonons. In our case, I can repeat again with Plera.
Yes.
We have very good decoupling.
Yes.
So, and we are doing this, we start from similar structures with this series array of junctions for 7 terahertz. Power load is very small. Parameters are quite promising and optimistic. Oh, and we start to do some system with silicon lens for the beginning. So we tested and got some response. It's not enough. It was 4 Kelvin response. It should be around 30 Kelvin for this frequency, I mean, Planck's peak. Then we met some problems in the zero due to column blockade, and we start to realize some modernization. You see, there are again 4 segments for different polarization, but for that goal we need to receive both polarization by one system. And so far, using this system, we could not do it because it's a single polarized antenna. But FieldMOScope said, no, we should combine them. And our plans were to combine this array and this array, again, over cross, and so complicated system with isolation layer. It's quite complicated for technology. And I started to think, could we combine both polarization for one bolometer to have both antennas? And final decision is this one. 45 degrees, one line is one polarization, another line another polarization, and each bolometer will be a sensor for both polarization. It was psychologically quite difficult to arrive to this idea. Now it looks clear, but I thought in orthogonal way, and I didn't show, but there were many different realizations of these structures. But as I try to do it in this way and combine with this polarization for the same bolometer, it was some ugly and not perfect. Final step before final realization was this one. It's almost decision already, but you see still 2 bolometers for 2 paths. Anyway, there was something already for 2 polarization. Now final decision this one, when one line here, one line for one polarization, another for the same, for another polarization, and each bolometer will sense this both signals. Quite effective, quite reliable again system, and quite good for further development for larger scale. So I plan to do analysis of the system for larger number of bolometers. It looks it also will be better and more promising to cut off amplifier noise and so on. So that means it's this one, it's another. It's another. It's already discussion about this 20 micrometers photon counter. We start to think. So you know, Goldsmith is doing this snake, long superconductor snake, and he is thinking about something bolometers combined with antenna. In this case, we should use many bolometers to fill some area, because size of these bolometers for 15 terahertz, 20 micrometers is 3 micrometers, quite small. Yes, we should fill some area, and then we should combine all of them, and they should weigh photons. Then one should be excited, and some photons should be registered. Not so easy, because it's large system, and what will be noise and combination and so on. We start to think, and it looks one option is this bolometer, so-called thermoelectric bolometer. It reminds CB, but it's a little bit opposite. We have superconducting absorber here, and we have normal metal here, and two junctions. This electrode only for protection, to avoid escaping of this electron from this superconducting absorber to this part. That means one way for electrons and holes to tunnel to this normal metal. Tunneling is open, probability is unity, I mean no usual tunnel barrier, resistance is not so high, all is good. But all this operation is based on imbalance of electrons and holes. We can create this imbalance or here in superconductor due to some maybe ferromagnetic impurities or any other recipes, or during tunneling through this barrier. If you manage to do it, it's very effective, very quiet device, and feature of the device, no bias at all. This is why we start to think that it's simplest and good. And with superconducting absorber, that means it's quiet. If you don't touch it, the absorber would not create noise. If you touch by photon, of course it would create noise and so on, will show reaction. But if you have many of these bolometers, of course it's good to have superconducting absorber to avoid any summarizing of noise from absorber. So it looks good. Only one question to realize this high imbalance. How can we do it? It's just comparison again, TEB versus CB. So, and I mentioned very important feature of CEB, quiet superconducting absorber. This is interactive things. Then, of course, several other good things. Ideal cooler, because it would permit to tunnel electrons and holes without any problems. Dissipation V square divided by R is also quite good, because it would be concentrated there and so on. But only one question, imbalance. And we've made some progress in this direction. It's good just for superconducting absorber with relatively high delta. There is comparison of aluminum and aluminum, and it shows that it's better. And for 7 terahertz, it's quite good to have this spare part to increase frequency of photons, to have more quasi-particles and electrons, and have their imbalance. Imbalance for tunneling. For tunneling through this barrier. If you have larger delta, it's easy to realize. So, and we are thinking about maybe this realization and the other, and one option is this one. So we have parallel connection of many bolometers. All of them are without bias. We only collect voltage, and we are waiting. They are quiet, zero bias, no noise, nothing is happening. And then if photon is coming, it would create very effectively high impulse here. That means it's jump to H omega, heating, and then we will collect some voltage due to tunneling of these electrons and holes. The way back through leakage resistance. Usually we have ratio around 1000, but if we use, let's say, 100 bolometers, it will be decrease of this ratio, let's say 10. Now maybe we need to have higher ratio to have better realization of this system. In this case, it could be realized and we can think about this. So, and that means this topic also in the field of our interest and the field of interest of Kardashev for millimetron. So, and finally, in conclusion that we are moving to a larger scale of array, and we expect decreased contribution of the amplifier noise. This is one of the main technical goals, but very important. Improving fluctuation sensitivity, its final parameter for observation, delta t, and improving polarization resolution due to high scale that today was confirmed by simulation of Stanislav. No, some applications for boomerang, for spike, and so on. And maybe also we can include for Olymp. So that's all about this part.
Looks enthusiastic, impressive, yes.
Yes,
Yes.
but it's reasonable to be enthusiastic about
Yeah,
this.
of course.
Yes, very interesting.
Very, very interesting because as seen from the final user, which I am the final user
Yes.
of this thing, they look way easier to use than other detectors.
Yeah.
And of course there is lots of technology which you know how to do because
No, it's our problem, our headache. But if you manage to do it and if it's
Yes.
working, in this
Yes.
case,
It looks
maybe
very, very
using
robust.
this room temperature amplifiers and all
yeah,
this.
that's so wonderful.
Yes,
Yes.
that's our goal. Demonstrate.
No. What can I say? I mean,
Andrei,
it's very
may
good.
I also one small addition? Maybe this addition is very close to my question to you in Palermo. I've asked you, if you remember, about how to solve problem of spectrum polarimeter for millimetron.
Yes.
You've told you are ready, but who will be manufacturer of our bolometers? Quasi-optics, you solved it, no problem. And who will be in this part of work? And
Yes.
I hope Leonid with our team are ready for this. And it's maybe for our next talk on Friday. On Friday, we'll meet with academician Kardashev, with Astrospace Centrum people. And I hope to tell together with you that now we obviously see a team that can provide millimetron by a proper spectrum polarimeter, matrix spectrum polarimeter. We have people who know how to make quasi-optical part, and we have people who know how to make bolometers too. Yes?
Yes.
Yes.
Okay.
So, as speaking about this, just for a while, our approach is to have a Fourier transform spectrometer
Yes,
because
yes.
it's a differential instrument which is very important to pick up very small fluctuations on a large background. And the disadvantage of this approach is that the background on the bolometer is very large.
Yeah.
For example, if we wanted to cover the 100 to 600 gigahertz band, either we split the band in several arrays, or the background will be very large, okay, and this will spoil the performance just due to photon noise. Will spoil the performance of the low frequency part of the spectrum.
Yeah.
So with this kind of design, there is no way we have to split the total coverage in 4 or 5 or 6 sub bands.
What frequency range from?
Say, for example, 100 to 600, 700, depending on gigahertz, okay?
From 100 to 600.
Yeah, in principle, we could do 100 to 1 terahertz, okay? In
yes.
principle, we could do that, and there are several drivers towards a high frequency. But
Yeah.
the higher you go, the highest you go, the highest is the background, and
Yeah, of
you have
course,
to
yeah.
introduce more bands, more sub
Yeah.
bands. So, from the point of view of the science, having a high background is a problem, because the final sensitivity of the system is not so good. Okay, and there is nothing you can do, even with the best bolometer technology. You can't do anything. The advantage is that with the same instrument you cover a very wide band. So, for example, if you are looking for carbon monoxide lines in molecular clouds, you do all the transitions with the same instrument.
Of course, yeah.
Okay, and so you have a perfect understanding of the physical conditions of the molecular cloud, which is important. If you do the Sunheiser-Dovich effect in clusters, you have the negative, the zero, and the positive part, and you have so many different frequencies that you can separate very well the different components of the signal. You separate the Sunheiser-Dovich, the thermal one, the non-thermal one, the interstellar dust, and so on. So it's a bit different in the sense that the background will be quite high for each of these bands. But from the point of view of the detectors, I think this is an easy system to supply, because the background is high, the bolometer noise will probably be negligible with respect to photon noise.
Yes, I think
And
so.
the architecture can be simplified, because you don't have to reach those extreme performance of 10⁻20
Yes.
watt per square root hertz, and so on. So I look forward to see this stuff.
So, for total...
to me, it's not clear who will decide which detector to use, because I'm unable to do the detectors. That's the only thing I know. And this has to be a discussion in the collaboration. I don't know exactly how to, because I don't know about other providers, of potential providers of bolometers for this mission. But what I see is that the technology you have is perfect. So why not? So
we can do any
and
combination.
To add more is simpler than all the other technologies I see. That's the winning point.
Yeah, we are looking at the most simple and straightforward realization. One question. As I understand from this wide band, of course we have quite high photon noise, but it's principal question. We can realize that amplified noise will be less than photon noise. And then question about experiment itself. Is it okay for whole experiment to do it in this level?
Well, depending on the targets. If you want high spectral resolution, this is not the good way to go. I mean, this is an instrument for low spectral resolution, or medium spectral resolution, of the order of 100 at 300 gigahertz. So, spectral resolution of 3 gigahertz.
In this case, we don't have problem with this high photon noise.
Well, it's a problem, but the signal is very large per resolution element.
Yes.
Okay, so the signal to noise is good in the end.
Yeah.
If you want to see narrow lines, this is not the way to go.
My question about this photon noise or signal. If we cut this bandwidth, it will be smaller power load and smaller photon noise, or not?
No, because in an FTS you have all the frequencies together.
All the frequencies.
You don't split. Every time you have the full
you
background.
mean full signal high.
Yes.
And on the phone of this part, you start to do analysis of
Yes. Yeah. So you don't escape. This is an instrument for.
But this is more principal problem of FTS.
Yes.
You should maybe more think and decide what is better for realization. Because we only can follow, we can do detector with noise less than this whole photon noise. This could
Yes.
be done, but then
Yes.
it's question
Well,
of the experiment itself.
the experiment itself has to optimize the sub-bands, okay? Because we will have dichroics, so that on each of these focal planes, one for each sub-band, we will get only a 1 octave, for example, of frequency, okay? From 100 to 200, 200 to 400, and so on, something like that. Well, this has to be optimized. And, but the big advantage of this instrument is that it's differential, in the sense that you have 2 input ports. You put the 2 input ports side by side in the focal plane, and so you put your target on one of the ports, and you have the background on the second port, and you measure the difference with the high rejection of the common mode
Yes.
by itself. So, for example, if you wanted to measure the spectrum of the Sunyaev-Zeldovich effect, there is no way to do it with a dispersion instrument like, you know, there is no way to do it with a Fabry-Perot instrument. There is no way to do it with the heterodyne spectrometer, because the bandwidth is too narrow, and so I believe this is the only way to do it. So this decision has disadvantage in the sense that the sensitivity is not extreme, has advantages in the sense that it's best suited to continuum radiation, like the Sunyaev-Zeldovich effect, and it doesn't require incredibly difficult detectors. So there are 2 advantages. So maybe I can, well, maybe on Friday I'll try to explain this in a more ordinated way.
I
But
think
this
the
is,
problems of FTS we should better to discuss on Friday. So.
yes, yes,
Okay.
yes.
Okay. And maybe 20 minutes left. Maybe we should start discussion the next topic. You specified it as readout system problems. Our guys also analyzed the problems of readout system
Yes.
of Boomerang, and our colleagues asked about it, some questions.
Okay.
Now I think we can only indicate our questions.
Let's see.
And maybe we should discuss them tomorrow in more details.
Yeah.
Yes, guys, are you ready to indicate our problems? Okay.
Some was lost without electronics.
Yes.
We have also made the system for testing our bolometers. You saw this amplifier box. It's our third iteration. We changed the amplifiers type. First we start with OP amplifiers. Now we have AB 745 amplifiers with optimal mismatching, noise mismatching with this type of bolometers and our amplifiers. We have also a multiplexer part to spend our time while testing the structures. And after the task is 90 channel readout receiver, we start to calculate number of wires that we need.
Yes.
Each
Yes.
channel needs 4 wires. We have 90 channels, and each channel has 2 polarization. And we were really scared this number.
Okay, you say 4 wires per channel
Yes.
because you want to make a 4 wires measurement, right?
Yes.
Is this absolutely needed or not?
No, if we use current source, we maybe I need. If we use current source for our bolometers,
Yes.
we can use it 2 lines for all matrix. Yes.
Yes, we can
We can
use
use
the current
one,
with the
and
scheme.
then we put resistors on
Yes.
wave,
Yes.
Yes.
and we'll supply by current each balloon.
And for each balometer, we need 2 lines.
For the voltage.
Yes.
Yes, but now if you decide the load resistors, okay, and you put them on the chip, then you cannot change the bias point for the
Yes,
different
of course.
detectors. So how uniform is the array? Because if the array is very uniform, you find that the best bias for one bolometer and is the best for all them. But if it's not uniform, you have you optimize for one and the other are not optimal, right?
Yes.
So the possibility to use just one current is in
Yes.
reality is a problem of uniformity of the array.
Of course, but fortunately we'll do it on the same wafer.
Yeah, so it should
Of
be
course, for
uniform.
different chips it's impossible, exactly.
Yeah.
For one wafer, no, we should check. We should check finally how will be uniformity and
Yes.
stability. Because we don't know, of course, this equation and
But anyway, the maximum is 360 wires.
yes.
That's the maximum. With this option would be 182. Okay, this is the best on the other side. Okay.
In this case we should check again. You mean 90 channels and each channel for 2 polarization?
I don't know. This is
Is
yes,
it-
you are
in this
right.
case it will be
You're
twice
right.
more.
Twice what I said.
What,
Yes.
what do you, I asked you already
Yes.
this question, you said that.
Yeah, no, two
to
polarizations because if we go without the modulator, we need both
Yeah, in this
polarizations.
case we need
700,
180 amplifiers,
Yes.
360 wires for voltage and maybe 2 wires for
Maybe
current.
two. Yes. Okay. Now 720 wires would be very difficult. I tell
Very
you.
difficult, yes.
Yes. 362 would be possible.
Yes, yes.
Yes.
No, I'm not sure. Maybe something. Several bytes. I don't know about uniformity and so on. Yeah. No, maybe later we'll check the uniformity of the system on wafer.
Yes, and also the bias. I mean, the responsivity versus bias is not very.
No, in voltage, no.
Change.
In current, it depends on quality. Yes, maybe it's not very critical. We'll see. Yeah.
But my suggestion is just to make a simulation to see how. I mean, based on your experience,
Yes.
you can guess which is the mismatch of the different pixels. Okay,
Yeah.
and then we see if from the measured VI curve you measured on your how much you can move the bias without losing more than 5% of responsivity, something like this, right?
Yeah.
And if you find that there is a large range, that then it's fine.
Yeah, yeah. So we will see this situation later because so far we are doing separate chips and
Yes.
don't have this information.
Yes.
So when we start to fabricate whole wafer, and in this case we can compare this parameter.
Anyway, on our side, we should be prepared to have 360 wires at least. Okay, this is the.
So from our side we will try to do it for this one bias for all. But if you fabricate whole wafer and separately check the parameters, we'll see what is this realization. You know, in voltage it's not sensitive. In this scale it's quite smooth.
Yeah, it's
but
smooth.
we put current, and in this case it depends on this ratio and how the differential resistance. Now we will see. At least this parameter is good. These parameters, and that I mean in voltage,
Yes.
the responsivity that you are
Yes.
thinking about. This is good. The rest we will check.
the hydrostat is actually suitable for now for 440 wires. That
Yes,
one,
that
if
one,
you want
yes.
to use that one.
Yes.
Total.
So this is what we have. What we have at the moment, 440 wires.
Is the total wires?
440.
Yes.
For both
Total.
systems, yes. For
Total. That's the
Total
total in
wires,
the wired in the
including
cryostat.
including cryogenics.
Including thermometers and so on. But,
Not many of them.
Mhm. Because it, I mean for two channels 150 and 300. Yes.
That's all we have.
Mhm. Okay. At least we know now and
Yes.
we'll think
Yes.
about how better to arrange.
But,
No, in not successful case, we should do this separate bias supply, and in this case, maybe we should increase number of pixels. In that case, I mean.
Yeah, but you know, the focal plane size is. I mean, the size of the focal plane is that one. We cannot add many more pixels.
No. About pixel, I'm discussing that if we realize that there should be 4 wires for each pixel,
Yes.
in this case we decrease number of
Yes.
pixels and
Understood.
effectively used. Yeah.
Yes.
No, we will check it, this question step by step. And I hope maybe it will be always not, because anyway, if you have so many pixels, it will be quite difficult to do different bias supply for each pixel. It's quite, I know.
Well, you need an automatic procedure to optimize.
No, an
and,
automatic, maybe. No, okay, so we will see. At least now we realize this question, have in mind, and we'll check uniformity of these parameters on whole wafer.
Yes.
This is one of our tasks. Right.
The second advantage of usage to wires for current, when one of pixels will burn, we will lose all the matrix.
Yes.
Why? Could you repeat again?
If one of pixels in matrix will burn out, in case of current only on 2 wires,
Yes, why?
we will
Why?
lose some of the matrix. We will lose.
No. Why?
But if you
We
have
have-
the dividers
we
on
have-
the ship, no.
No. It's wrong. No. We have 2 wires and then we have 180 pairs of resistors.
In this case, yes.
Yes.
Having considerably higher resistance than resistance of the
If
structure.
for one,
No, it's wrong.
if the wire fails,
Yeah.
you lose the matrix. Yes.
The wire will cut. Will be cut.
Why?
You lose.
Huh?
If the wire fails, yes, but
is-
anyway, we put 2 wires, for example. It's an important one. Yes.
So here is some possible realization of multiplexing. The first is the same as we have now. It's only 360 wires goes to amplifiers box,
Yes.
and then multiplexing before ADC and control electronics with special software and so on. The second approach is first multiplex somewhere in cryostat, maybe if we have enough power budget. I don't know, maybe with relays. We know that some relays don't need power to be switch on. We just put the signal and the relays are switching and stay in this position.
Latching, really.
Latching, yes.
Yes.
Maybe this will help us.
But how often you have to multiplex the system?
This is the question in the next slide.
Okay. Okay.
So here is clear.
Okay.
The next slide, please. here's with some possible compromise solution. We just divide this scheme on some parts, and when we have trouble in one line, we lose not all the matrix, for example 10, 20, and to choose some compromise solution.
Yes.
It's it looks better at this time. So the another equation is some initial equation about frequency of sampling on the
Yes.
end of electronics.
Yes.
How often it should give data from the electronics.
So this I can answer as it is, because the experiment will scan the sky, okay, with some speed and with some angular resolution, which is at this frequency should be about 4 arc minutes, say. Okay, so the 4 arc minutes in the sky, and the scan speed is say 1 degree per second or so. Okay, so if I can write here, maybe. So this is our beam, and is about 4 minutes. This will move on the sky at the speed of 60 minutes per second. Okay? So, if you wanted to take minimum 3 samples per beam, minimum, okay, you have 60 by 3 divided by 4 samples per second. Okay? So this is whatever it is, 15 by 3 is 45 samples per second per channel. Okay? So this is the typical sample rate that we need. Okay? Which is, if you multiply by the number of channels, it comes a sizable number. Okay?
This is in case you don't have also a rotating.
Well, yes, in case we don't have the rotating. But anyway, if we have the rotating halfway plate, will be in steps, so it will be the same.
So you're not thinking.
Well, I'm
the
not
one
thinking
that
about
continuously-
doing a very fast modulation because
It's other mode.
not very easy to do. So more or less 50 samples per second per detector. So it's
It is very
fast.
important.
You cannot do it by latching
Wait,
place.
yeah.
No way.
Okay.
The next question is, should we use DC biasing or DC?
Yes.
I think we should. In first approach.
Yes.
And
But we need several bias oscillations per sample.
yes.
Okay? Which means that the bias frequency, the AC bias frequency should be, say, 200 Hz or so, minimum. Okay? Now, one problem with this is the capacitance of the wiring. Because we have, as I understand, we have a schematic like this. We have, I don't know which is the symbol of the CEP, but anyway. Okay, so we have, we measure delta V, and we have these two load resistors, yeah? And we supply the AC bias, okay? And here we have the stray capacitance of the wiring, okay? And the stray capacitance of these wires can be something like 100 picofarad or so. Okay. Because the wires are long and they are twisted, and so they are very thin. So when they are twisted, the capacitance is not small. It's not small. Yes, it's typically 100 picofarad or even 200, something like that. So these sets, you cannot use a high frequency bias depending on how much the load resistors are. Because if you are in the 10 megaohms range or 100 megaohms range, depending on, sorry, the wires are, these are the wires, resistance, and this is on chip, as I understand, right?
Yes, yes.
Okay, so this is very small, this is large.
Yeah.
Okay, this one, this capacitance is,
Yeah,
is 100
exactly.
picofarad. Okay, so you have 500 ohms or 1 kilo ohm times 10 to the minus 10 farad. Okay, time constant. So not a problem.
No, really it should be bias resistance on chip. If you don't chip bias resistance.
Yes, you need it
It's
because
not always.
otherwise is a problem. If you put the load resistor at room temperature, it's a big problem.
Yeah.
But if you do this way, is okay.
No,
Time
I
constant.
mean, our suppose system that we have something around, let's say, 2 mega ohm or maybe 10 mega ohm resistors on chip. In this case, it will be a little bit harder. Let's say 10 mega ohms.
Okay.
Here.
But that's fine. I don't think there is any important capacitance on chip. So I don't know.
No.
You might know.
Yes, yes. No, yeah, you're right. You're right, especially if we do divide, it will be even easier. No, it's not serious problem.
Okay. Good. Sorry, I was trying to understand if
Yeah.
there was a problem or not. So, the other problem using higher frequencies for the AC bias is intermodulation on chip. Okay. So here we have the other detector. Okay. Okay. So you bias with the same voltage, and then you have these dividers. Okay. And there will be some stray capacitance between the two channels. And so if you use high frequencies for the bias, you have intermodulation, okay, crosstalk
Talk of channels. Yeah.
between channel to channel.
Mm-hmm.
So that's why I'm saying a few hundred hertz, not more than that, to avoid these kind of problems. But this should be checked once we have the array and we see which is the stray capacitance on the array. Channel to channel.
Colleagues, time. Unfortunately, concert will start and we should go. Have you more slides?
Yeah, another one.
Yes.
Just another one.
Yes.
Another.
I hope.
Yes. No, I mean, that part can be decided later, I would say.
Yes. I hope
You
we
want
finish.
to-
But we can speak tomorrow for a while.
Yes, yes. Not only tomorrow. I hope our team will arrive to Roma and to discuss it near the real system to see how such problem solved in your Boomerang 2 and probably to discuss the next stage. Colleagues, thank you. I have to interrupt you and have to pick up my guests, my team, to the concert. Thank you.
No, thank you all very much, because
Okay.
what I've seen here is impressive. You will work, group work so nice that it will be a pleasure to work together, really.
We do definitely, and I hope I see you tomorrow after your talk, just here, and hope to finish our discussion. Okay.